All right, so this is a very exciting day for multiple reasons. We start our descent into the final part of the class, and I really hope that the way in which I've designed the material and I've been working on this sort of structure and sequencing of topics for the last few semesters. I really hope and I think in many ways and expect that the way in which the class sort of ends up is really going to feel like a nice sort of closure in many ways to the class, sort of solidifying some of the loose strings, if you will, that we have still sort of lingering out there. So, and then the other part is that the discussion conversation, the Solow-Swan model that we're going to introduce here and then discuss for the majority of this week is one of my favorite things to talk about. It's I know I've said that a lot this semester, and at a certain point you probably question my sincerity, but this is certainly one of these kind of economic ideas that when it was sort of exposed to me, it really was another sort of economic model that I thought was the perfect balance of complexity, but also explainability. So you can sort of sit down and I think work a lot of people through this particular model and engage them in a conversation ultimately about sort of how do economists think about economic growth and what do we think sort of defines how a country grows over a very long time period. And this is, I think, in many ways, what a lot of us originally, we thought we were going to get into economics and we were going to, talk about economic growth, and because that is sort of the promise of economics, right? Is that it's supposed to understand the way in which a country grows, and then ultimately this becomes a part of, a policy set of recommendations that are supposed to sort of help to ensure the relative prosperity of a country. To me, that was always what economics really was or should be about. It should be about, giving us the best chance at having the least worst economy kind of possible. And so the Solow model is really important because it is a model that, like a lot of the stuff we've done, discussed this summer, is certainly within kind of the canon of how we think about the economy operates, and in particular how we think the economy operates over the very long run. So let's just work through, I think, some very basic parts of the model. I'll set up the basic graphical representation of the model, and then we'll work through a very simple numerical example, and then we'll kind of stop it there and then move on and complicate things. So the big sort of thing with the Solow model is that we don't hold anything really very fixed in the economy. So in the neoclassical Keynesian models, there was always something fixed, capital or labor or even both were fixed at particular stocks. We're not going to think in terms of sort of stocks of capital, stocks of labor, and then ultimately a stock of output. We're going to think very much in terms of flows. Now, the sort of connection here with maybe some of your previous training and principles of economics is very similar to the way in which we think in terms of fixed versus variable cost, right? So in the short run, things are fixed. And we can think about that in terms of sort of the way we have described rigidities in the economic system. So over the short run, there are all these what we refer to as nominal rigidities. They're not sort of necessarily like real rigidities, right? For example, if we're talking about wage rigidities, the idea is that a big part of the wage rigidity is tied up in the pricing piece of that, as opposed to the actual marginal product of labor. It becomes a part of the value of marginal product of labor ultimately, and so we can have these sort of nominal sort of considerations that cause the economy to just not be fluid, or perhaps not be as fluid as we think, if we instead envision an economy over a very long run. So it's not arguing that we're going to take the economy and make it completely non-rigid and completely flexible, but rather that we're going to extend the time horizon of our conception of the economy. And in doing so, one of the natural consequences of that is that we start thinking in terms of variability. So everything here is a flow as opposed to a stock. So, and that carries over into our conversation with respect to the production function. So we're going to have a very similar production function to the one that we've had all semester. In fact, we're going to go ahead and make the assumption that we have Cobb-Douglas. The nice thing about Cobb-Douglas, production functions, of course, is that they have constant returns to scale. That's a nice theoretical assumption for us to make, but it also ends up being a fairly nice empirical assumption. If you look at physical capital, it really does seem empirically that physical capital seems to operate with respect to constant returns to scale. Where you get some sort of interesting divergence from this is with respect to is with respect to human capital. So one of the arguments that we'll make towards the end of this week in the conversation about endogenous growth models is that maybe human capital has even increasing returns to scale, and that sort of the ramifications that might have in terms of how we think about the macroeconomy. So we're going to assume just sort of a basic Cobb-Douglas production function. Y equals, some function of capital and labor, and then we're going to give it this Cobb-Douglas form. Now, one of the key ideas here should feel very comfortable to you, and that's we're going to continue with the idea that savings equals investment. We're going to end up thinking in particular about a savings rate. And so the idea is going to be here that the economic system in question has a particular level of savings, a savings rate. And so we can think about sort of the extent to which the economic system saves its output and then uses that for investment. So you can think about, there's an amount of income being generated, an amount of output being generated in the economic system in a given year, and then there's going to be a savings rate for that country, and so the proportion of output that is saved is going to be reinvested in the economic system. And so in a sort of specific functional form way, we can think about investment as just being the savings rate times output. We'll detail a little bit kind of what that means practically here in just a moment. And then to just sort of like set up the most basic sort of production function, investment and savings component is that we're also going to think about things in terms of consumption. So consumption, ironically, I think ends up being a really important part of this particular model. In fact, one of the key ideas that we're going to get to in later videos directly relates to the extent of consumption going on in an economy. And I want to point out just sort of real quickly, because oftentimes we can sort of lose sight of this fact, but because we're talking about economic growth over the very long run, and because ultimately we're going to tie this back to the level of consumption that is going on in the economic system, the Solow-Swan model ends up being a model really about quality of life in many ways. So the idea here would be is that we're interested in how an economy grows over the long run because economic growth makes people better off. And the way that we're going to sort of confront that particular idea is ultimately to consider consumption. Now, that of course boils down human prosperity into economic transactions. But we're economists, right? That's what we're sort of supposed to do in many ways. Now, what does this sort of mean in the context of a graphical representation of all this stuff? So again, the graphical representation here should end up feeling very comfortable. Now, one of the things that we're going to do is to make our life a little bit easier, because we do have the two factors. And if we want to sort of truthfully consider the two factors, then we would sort of need to have a three-dimensional consideration, because you have the output Y, and then you have the two inputs, capital and labor. And we don't want to deal with any sort of three-dimensional conception here. So we're going to make it two-dimensional. And the way that we're going to do that is kind of interesting here. So we're not going to think in terms of output or capital in this model. Instead, we're going to think about output per unit of labor. We're going to think about capital per unit of labor. And this has some nice mathematical simplification to it, but it will have also a very practical reason that we're going to do this a little bit later on. So just to kind of really quick sort of take you through what we're doing here is we start with a production function y is equal to, and we'll just say k alpha L beta here, just, and then we could, if we wanted to here, make the classic Cobb-Douglas assumption, which would be that alpha plus beta equals 1, right? We don't have to make that assumption, but that's usually the assumption we make. Here, it's not really that important at all, as you'll find out. So we want to take this production function and we want to turn it into a per worker production function. So we're just going to take y, we're going to divide by L. And then so we then distribute an L through the production function here. And so what we get is capital divided by labor raised to the alpha, and then labor divided by labor raised to the beta. You can see that's going to drop out because that's going to end up being 1. And so then what we end up being left with is we have y over L is equal to k over L. And then again, we're raised to alpha. And then what we're going to do is we're going to define a small y as output divided by L, and we're going to define small k as capital divided by L. And so ultimately what we can do is we can rewrite the production function as just y is equal to, in this case, k to the alpha. So this is how we get to a per worker production function. Now, what this is going to enable us to do, again, is to put everything into sort of the two-dimensional space. So let's get rid of all this. And then we're just going to have a very sort of classic production function like that. And we're going to have capital per worker on the horizontal axis, and then output per worker on the vertical axis, right? And so the idea here is that for any given level of capital per worker, this is going to define a level of output per worker. Okay, now the second part of this in context of the production function is that savings component, which again translates into investment. So the way that we're going to think about this again is in terms of rate. So we have y is equal to k raised to alpha here. That's our basic production function. And then we're going to have an investment function that is equal to s times y, which is just going to be s times k to the alpha. And so this defines the level of savings in the context of investment. And so now, or in the context of output. So now for a given sort of output per worker, or capital per worker rather, we can take this up, and then this is going to define for us a level of investment and then also a level of output. So we have a level of investment, we have a level of output. And then again, going back to the fact that we're going to ultimately think about this model in terms of consumption as well, we can see that the difference between output and investment is going to be consumption. So you have kind of the full conception here, right? We have output, the economy saves some fraction of output each year. We're going to frame output in terms of capital per worker, just out of simplification. And then again, for a given level of capital per worker, it's going to define an output per worker as well as an investment per worker. And then we can use that to then define a consumption per worker ultimately. Yeah, so one of the things we're going to care about eventually here is the extent to which we can try to maximize consumption even. Okay, now let's go back to the kind of basics of the model, and let's add some stuff to it. So typically in the Solow-Swan model, you at the very least, it always includes depreciation because and I mentioned this way at the beginning of the semester. The thing about capital is that you don't really own capital. You're sort of constantly renting capital because capital, in terms of like economic value, is always depreciating, right? The classic, you buy a car, a brand new car, as soon as you drive it off the lot, it depreciates in value by 50% or whatever the percentage is that people like to claim is the actual correct one. Um, so depreciation is really important here, and the way that we're ultimately going to think is that there is at any given time a flow of capital in to the economy and a flow of capital out of the economy, to the extent that we are going to think in terms of there being a capital stock, but that we're going to think about the dynamics of, for any given year, is that capital stock being added to, or is that capital stock being taken away from, or is the capital stock staying exactly where it was last period? That becomes a really important part ultimately of this entire process. So the idea is that for a given year, the economy invests in a particular amount of capital. Again, we already saw that savings times output. And then for any given year, some of the previously held capital is going to depreciate out, and therefore no longer sort of shows up and is no longer a productive part of our economic system. Now, we could stop it there, and the sort of maybe most basic form of the Solow model would sort of stop us there. But we're going to add to it something that you would eventually add to it anyway, and I think it's good to go ahead and put it here. But we're also going to add population growth to the Solow model. And the interesting thing about population growth is that it ends up functionally being equivalent to depreciation, in the sense that as more and more people get added to your economic system, the capital per worker is sort of naturally declines. So when we think about N times K, the population growth times K, that's basically the amount of like used capital or occupied capital. One of the interesting dynamics that we're going to sort of illustrate in the context of the Solow model eventually is that technological growth does some really interesting and counterintuitive things to the sort of overall productivity of an economy. So an economy can become more productive, but then in terms of capital per worker, we get these sort of interesting and like I said, I would argue at times fairly counterintuitive outcomes. Okay, so let me bring back my whiteboard here for just a moment. Sorry. Okay. So go back here. All right. So we want to add this to the model, but the reason ultimately that we want to add this to the model is because depreciation and population growth are going to affect the sort of economic usability of the capital stock, right? Both in terms of there being sort of workers utilizing units of capital. We get a very basic production function kind of argument here, right? Think about the economy as a big sort of box with a turner on the side. Capital and labor go into the box, capital and labor get combined in some way, and then what comes out is output, right? So you can think about sort of units of capital being used by units of labor here. And so again, the dynamics of kind of what population growth does then to economic growth, I think is quite interesting. So, okay, we're going to bring back the basic idea that we've already established here. Again, capital per worker on the horizontal and output per worker on the vertical. Let's put our production function there. Let's put our savings function there. And then what we're going to add to it is what I've always sort of referred to as the depreciation line, although here it's also going to include that kind of population growth component as well. So it's sort of depreciation plus population growth. So let's just add a straight line there. That's supposed to be a linear line. So if it's not quite, forgive me for that. And then so here we have depreciation delta plus n times k. So the extent to which One, capital is depreciating, and then also the extent to which capital is being used by new labor is the way you want to think about it, right? So depreciation and population growth. So now what we have is the most important sort of idea, the central idea of the basic Solow model, which is that our economic system now exists in this sort of steady state idea. So if we look at this point right here, let's just call this point A for now. So at point A, what we should see is that the investment in the economy is just equal to the amount of capital being depreciated and used. And so we would refer to point A here as an economy's steady state. And the idea behind steady state is that the change in capital per worker is zero. So year over year, the economy is neither adding to the capital per worker stock, nor is it subtracting from it. The basic sort of vernacular here is that if the change in capital per worker is greater than zero, then we refer to this as accumulation. So capital accumulation for obvious reasons. So capital accumulation. And then if the change in capital per worker is less than zero, then that we typically refer to this as capital shedding. So the economy sheds capital if its depreciation plus population growth is greater than the level of savings. And so you can see that in the Solow model, the idea is that the savings in the economy is putting upward pressure on the capital stock. The level of depreciation and population growth is putting downward pressure ultimately on the capital stock. And then the idea here is that the economy is moving at all times towards the steady state, right? Because if you think about it, for levels of capital per worker beyond the steady state, so let's just call this, we'll call this high, for high levels of capital per worker. Well, if we go up to the model, we can see that we hit the savings function below where we hit the depreciation line, right? So let's call this B and C. So from B to C, you can see that the economy is depreciating out more capital than it's investing. So that means that from this period to the next period, we're going to have less capital stock per worker than we did previously. And so we're going to be moving towards the steady state. You know, if we're over here, we can call this capital low. And you can see here depreciation, which we'll refer to again as C, and then investment, which we'll again refer to as B, is the opposite. So now we have more capital showing up in our stock than is instead being depreciated out. And so there again, we're moving towards the particular steady state. Now, why does this matter? What is the sort of broader point of all this? Well, in these movements between capital stocks, you're getting changes to output per worker as well, right? And so what we sort of put this on ultimately is that the sort of movement of the economy towards its steady state is ultimately going to affect its economic growth, to the extent that if an economy is sort of overshooting in terms of its steady state, then we actually expect output per worker to decline, right? So for capital per worker H, we would have a level of output. We'll call this YH here, very high level of output. But if we move towards a steady state, of course, we can see that we're going to get a smaller level of output. We'll call that K star and Y star for steady state here. And then, of course, if we're in the low part of our capital stock, we're going to get less output. So we'll call that YL. And so we would get a greater growth. The idea here is that the economy may want to naturally grow, right? That may be a thought that we have. But what Solow and Swan argued was that it's not so much about the economy wanting to grow, but it's about the relative capital stock changes over time that seem to be the main determinant as to how a country grows. to the extent that now we get to have a clearer idea, not just by the way of what countries are growing and what countries are not, but why are some countries growing quicker than other countries. For example, the U.S. economy, we've had, in good years, 3 to 4% economic growth over the last 30 to 40 years. If you compare that to, for example, the Asian tiger countries who had economic growth rates 15, 20% in some of those particular years, we that might be somewhat of a puzzle, right? Why did the Asian tigers grow so much more rapidly than the U.S. economy did during that same time period, despite the fact that in that time period, the U.S. economy continued to be the dominant economy in the world, and certainly was the strongest economy in the world back at that point as well. And of course, the sub story is that the U.S. greatly benefits from the Asian tiger, a situation. That explosion of economic growth certainly benefits the U.S. economy as well. But the story to that is really straightforward in the Solow-Swan framework, which is that basically they were much further below their steady state than the U.S., right? So the idea is that an economy is always going to be growing when it's below its steady state, that the reason why an economy stops growing beyond any sort of exogenous shock that we've talked about would be that it's reached a steady state, right? And so once you reach the steady state, that's when we don't expect output to sort of necessarily grow over time. But we also don't necessarily need output to grow over time at that point because we've reached that particular steady state. But prior to the steady state, we're experiencing economic growth. And the further you are away from your steady state, the greater the rate of economic growth you're going to have, right? What is the rate of economic growth here? It's just going to be the slope of the production function, right? So you can see that as we move up the actual level of output, the slope of the production function declines. That means the rate of economic growth is declining as we get to higher levels of output. So one of the main reasons why smaller economies grow more rapidly than large economies is precisely because they are much further away from their steady states. And so their additions to their capital stock are going to be comparatively larger than our additions to our capital stock. And the additions to the capital stock is where you get a lot of this sort of economic growth, as it were. So let's cut it there for this first video. I think we got through a lot of what we need to get through. But sort of, let's cut it there in terms of theory. Let's just work through a very simple kind of numerical example just to kind of set up the idea here. And so let's go here. So let's imagine, we have an economic system that has Cobb-Douglas production function. The per worker production function is just the square root of capital per worker. Let's assume a savings rate of 20%, and then we'll assume that both population, this should be 5 here, population growth and depreciation are also 5%. Hold on, let me make that actually, there we go, 5%. So the thing is that we know what occurs in the steady state. The steady state condition is that the level of investment is going to be equal to the level of depreciated plus used capital for that given year. So what we can solve for now is we can solve for the steady state level of capital, because we can put the production function in terms of capital, and then what we're left with is, essentially 2 equations and 1 unknown. And so we just do a little bit of math here. And, again, we're creating the condition and then solving for the level of capital stock from that particular condition. And then so what you're left with here is ultimately that the steady state level of capital in this particular economy ends up being 4 units of capital. And what you will ultimately sort of realize about this process is what really ends up mattering here is just the ratio of depreciation plus population growth to the savings rate, right? Because you can see here, when we ultimately work through and solve for K, the ratio of savings rate to depreciation and population growth ends up defining ultimately what that steady state level of capital actually is. So you can see, for example, if the savings rate is much higher, then we're going to get a higher level of steady state capital, right? And we can see that, by the way, really simply in the graph here. So let's take, we have a production function, we have an initial savings rate. So we'll say S of K 0.5. This is K 0.5. And then let's say the savings rate, excuse me, sorry. Let's say the savings rate increased. And so if the savings rate increases, then we get that. So we'll do S prime K of 0.5. So the savings rate has increased. And when the savings rate increases, then the steady state level of capital is also going to increase as well. And so we started with this as the steady state level of capital. We'll call that K star. And then after the increase in savings rate, we now move to a higher level of steady state capital, as you would expect. So again, the model is pretty straightforward. Don't lose sight of the relative simplicity. Now, one of the things we're going to do in future videos is we'll go through a two-period model that becomes a little bit more complicated, certainly. And then just to put a capper on all this, we can then, of course, now that we have capital, steady state level of capital per worker, we can just plug everything in to solve for output per worker, and then, of course, consumption per worker. So at 4 units of steady state capital per worker, we get a steady state level of output of 2. And then if you just go through the sort of simple math, output minus investment ends up equaling consumption. And you can see that at 2 units of output and then a level of savings in the economy of 20%, that ends up being a level of savings of, in a sense, sort of 40 cents. And so ultimately, consumption equals 1.6 in this particular economy, which should make a lot of sense, right? If output is 2 and we save 20% of output, then that should make quite a bit of sense. So anyway, yeah, simple Solow model to kind of get us started, and like we always have, we'll complicate it. But to me, the beauty here is this relatively kind of simple framework, because now we can start moving stuff around, right? We've already shown here what happens if savings increases. Certainly, we're going to consider what happens if, for example, depreciation increases or depreciation decreases. And of course, there can be various reasons for this: population increases, decreases. Ultimately, we're also going to have a very interesting conversation about the extent to which, for example, this ends up being about policy, right? Savings rate, we might argue, eventually has something to do with central bank policy. And so, what is the central bank trying to do in the context of a country's steady state level of investment? So we get some really interesting conversations from that. But for now, let's stop it and then see you in the next video.